Hello and welcome to the next lecture in the course. Now if we just go on to the course and see what we've got. So we're looking here at an introduction to machine vision. So if I just open up the folder and I'll start from the beginning. So introduction to machine vision, and here we're going to go through some example applications. And there are four main application areas that I want to focus on and that we can use traditionally machine vision for. They are positioning objects, detecting presence or absence, measuring distances and angles, and examining objects, which can go into some depth. In our lab, we've got a specialization in surface examination, particularly with 3D defects. Now, just go on to the next slide. So starting off talking about positioning, and here we're talking about alignment or guidance of objects in the image. That could be simple things like electronic components being aligned on a printed circuit board, or robotic arm, as it says there, going through a particular path. And we're trying to check the movement of the object. Detection can be quite a simple application. It's really just checking whether something's there or not. One of the first machine vision applications that ever was implemented was by Ford on their engine production line, actually. It was just looking for a large clip on the end of the, I think it was the end of the camshaft, and it was either there or not. And it can be various characteristics on the part that you might be looking for. One example that we worked on was for a company in Cheltenham who were making synchronizer hubs for automatic gearboxes for trucks in the States. And I don't know if you know much about the manufacturing process behind one of these synchronizer hubs, but it's a broaching machining operation where you drop this big tool through the center of the hub and it machines out part of the profiles of the interior that you want on the hub. And if you don't get this in the right order, this broaching operation, or if you don't do it, then it causes a problem with the synchronizer hub, which can cause a problem in the automatic gearbox of the pickup truck. And of course, if you have to take the gearbox apart to replace that, you're talking about thousands of dollars of work for a part which is just a couple of dollars in value. So it's very critical. And again, it's a fairly boring sort of task, which humans are not particularly good at, but the machine vision is particularly good for checking the presence of marks on the hub in that case to show that the broaching operation had been done. Another example given there is manufacture of DVD-ROMs, just checking that the disc got the label in the right place, actually. Or it could be, I remember another application with a company we're working with called Scorpion Vision, who we have a good relationship with, was simply looking for labels on cheese segments, cheese slices that, those sort of slices of cheese that you get in the shops had to have the label in the right place, and just checking it was actually there. And you can do that kind of thing at high speed, as you're actually putting it on. You detect problems before they get worse, really. So measurement, and we're talking about gauging distances, angles, and other quantities, as it says there. And of course, IMAC comes with many, many tools in the, or you can call them VIs, that are sort of vision libraries that allow you to do various things, to measure various parameters in various ways, and all sorts of different scales, as well as it says there. Now, examination can take many different forms, of course. Examinations of objects can be all sorts of different ways of checking them. Could be something simple like what's the serial number. One thing we did was we were looking at aerospace components who were actually on turbines. You get these blades, and they need to take the turbine engine apart to check it at various times. And obviously, you want to make sure you put it all back in the right way. And they have these numbers sort of marked on them with 3D sort of punching operations. And we with some of our 3D techniques, were able to measure these punched figures and numbers, even in the presence of all sorts of light changes and marks on the surface. So we were quite good at doing that. That's quite a big problem, actually. Rolls-Royce have quite a big application for checking the markings on parts, which sometimes are not marked in a very standard way. So it can be quite a big challenge. So what are the critical elements of the machine vision system? Well, to get a successful application up together, we've got to put some emphasis on various areas. The first of which is lighting and optics. Might seem a bit obvious that you've got to light something before you're going to stand a chance of seeing it. But this is an area which is often overlooked, nearly always overlooked in books on the subject and overlooked in many courses, because it's absolutely critical. Without good lighting, you can't really get a good result. You can't take a poor image and do some fancy processing and end up with something brilliant. You're better off starting with the right lighting in the first place, especially if you're trying to recover color or complicated detail. The optics, again, is also very important. Having the right lens on the camera is surprisingly important, because if you haven't got the right lens for a particular type of light, maybe a wavelength of light you're using, then you might get a poor quality image because the light just won't be transmitted very well. We've seen this before now. Cameras, of course, that's the most obvious and critical component of the machine vision system, is a camera, I guess. And image acquisition, there's a number of ways you can do that. We'll talk about in LabVIEW, and a number of different speeds you can acquire images and synchronized with other operations, which we'll talk about. Then, of course, we've got to do some image analysis, which is where we need our software. And we can certainly do that in LabVIEW, and we'll go into that in some detail. To start thinking about lighting, this is, as I just mentioned, a critical first step. So what we're trying to do many times is we're trying to highlight the region of interest and diminish the appearance of the background. You know, we're trying to arrange for as much contrast between what we're trying to measure and background things in the image as possible, really. And if we use the right kind of lighting, we could certainly make that easier. So, as it says here, really, if we get the right lighting, it can save us a lot of problems, because poor lighting can cause shadows and glares, which you can just get rid of by using the right kind of lighting. Now, I've got a book, The Imaging and Vision Handbook, by a company called Stemmer Imaging, which we've bought thousands of pounds of equipment from over the years. So they supply me with many copies of these books. I'll try to get a copy of this book to you, because it goes into a lot of detail about different types of lighting technologies and what you can do with them, and all sorts of different background information. It's a lot more than just a catalogue of cameras. It's actually a bit of a book full of information. It's very, very useful for real applications. And I think it will help you with the assignment as well. So it'd be worth reading that. So spending time on selecting, as it says, and setting up lighting is time well spent. And that actually can save you a lot of work on the software side, because if you get this, as I was just talking about, if you simplify things by clever and good use of lighting, then you need less image processing as a general rule, which will save you time on having to do the processing on an ongoing basis, really. So the image features, of course, are also important. How big the object is you're inspecting, whether you can get it in field of view, we'll look at that. Is the object in motion while you're acquiring the images? And years ago, we used to use strobes if you had objects in motion. Nowadays, we don't need to do that, because the cameras are so sort of flexible, you can do so much with them, that you can just capture images very quickly. You can adjust the shutter on the camera and capture images very quickly according to exactly when you want to. So you don't really need strobes, which is just as well, because strobes involve complicated equipment, high voltages, possible radio interference, and it's a bit too complicated, by the way. So lighting sources and resources. The common types of lighting that we got here are listed there. Now, over the years, we used to use, over the last 20 odd years, of course, a lot of halogen or incandescent bulbs. But generally speaking, we're moving a lot away from that. And generally now, the lighting in machine vision is dominated by LEDs. And there's a number of reasons for that, which I could go into in a bit more detail. The most obvious one is that LEDs are very flexible. You can turn them on and off quickly. They're very efficient, so they don't heat up so much. So it's not such a waste of resources. And they generally got long lives as well, compared to halogen lights. There is one advantage a halogen might have over an LED, is that halogen light, or a conventional bulb, produces a continuous spectrum. Because the filament, a tungsten filament, is actually a black body emitting radiation at a temperature of 5,000 Kelvin. So it's got a continuous spectrum of wavelengths. So if you want a particular wavelength, you can always use them from a halogen light by means of filtering or just selecting certain wavelengths. Whereas LEDs have specific wavelengths, more short, they don't have such continuous bands, they have more discrete bands. So that can sometimes cause a problem. So sometimes you do need a continuous spectrum. So National Instruments, they make LabVIEW, and these are some of the partners, Edinburgh Scientific, Stockholm Yale, they make cameras and supply them. I've got on the bottom here Stemmer Imaging Limited, who we've had a good relationship with, as I say, and they're always willing to have a chat if we've got a particular application that we're interested in. There's also another couple of companies we have a very good relationship with, and that's Scorpion Vision, who supply a wide range of equipment, and also Alrad Imaging, who we've been working with for many years. These companies, because we work with them a lot, they're very willing to just lend us equipment, which we can either return to them or buy from them after we tested it. It can save us a lot of time and money doing it that way. So the type of lighting, as we've been saying, is pretty critical to the success of the application. As I was just saying, we're trying to illuminate the feature we're interested in as well as possible. It's going to be difficult if you can't do that, as it says there. And if we can do it, we can increase the signal to noise ratio of the camera. And one thing we do quite often, another source I should mention that we use a lot, is laser light, of course. Light amplification through stimulated emission of radiation, being what laser stands for. And nowadays these devices are also solid state, sort of electronic devices. But what we typically do a lot of the time is that we use a plane of light. So we have a cylindrical lens built into the laser device, which changes the laser beam and spreads it out into a plane of light. And that's very useful because we can shine it at, say, an object, and we can scan it over an object or put the object on a conveyor belt. This is a standard technique in 3D machine vision to recover data from 3D objects by scanning them by laser, we call it laser triangulation. It's quite accurate. It has a disadvantage that it's a bit expensive, the laser, quite typically. And, but it is accurate, and it's used quite commonly in industry. One thing you can do, I mentioned this because one thing you can do is to improve the signal to noise ratio, is to use a laser of a particular wavelength and then match that to the transmission characteristics of a filter. We buy lots of filters off various companies. And then the signal to noise ratio will be increased dramatically because a lot of the background radiation from various object lights in the lab or wherever will be blacked out because we're only looking for that wavelength with the lasers at. So that's a technique definitely worth doing if you're using a laser. So another thing we got mentioned there is object lighting position and orientation, and whether or not we got directional light sources. And as it mentions there, sensitivity of specular highlights. Specular means mirror type reflection. So if you get this mirror type reflection or specular highlights on the surface, it could be something like cellophane wrapping on an object, or maybe on something which has got a barcode on it. So you want to read the barcode, you don't want the specular highlight. So how can you get rid of that highlight? Well, there's a number of ways of doing it, but one way of doing it is to have diffuse illumination. So companies like Stemmer, they sell lights which have various constructions of LEDs, like a ring light is a favorite. You have a ring of LEDs and a hole in the middle, and the image is taken with the camera through the hole in the middle. But you've got this diffuse illumination, so it's not directional, and you're going to be able to minimize the highlighting in that way. And that's mentioned here, as you can see, the ring light is mentioned here. So strobe, nowadays you probably wouldn't bother with much. Backlighting is a simple application if you're looking for a silhouette. Suppose you're looking for a silhouette and you just want to get the area and shape, you could use backlighting. And so different techniques have different advantages. There's a lot more. This is just a few examples. So we're trying to separate the feature. Backlighting, as it says there, ring light I just mentioned. Another thing it's mentioned in here is polarization. Now, you're probably familiar with polarization to some extent, like Polaroid sunglasses. What polarized light means is that normally the light consists of electromagnetic fields which have all orientations, but when you polarize it, you're just polarizing it into one plane. The field is just in one plane, and this is called linear polarization. So the idea with the Polaroid sunglasses is that light is reflected from the surface of the swimming pool, say, and then this polarized light hits the sunglasses, which consists of polarizers, And much of that light will be cut out because it won't happen to be the same polarization as the glass is. So it works quite well, and it helps you to see under the surface of the water. Now, it's a similar kind of idea with removing glares using polarization. So what we got there is, say, cellophane wrapping on an object. When the light's reflected off that, reflection from a non-conductor tends to polarize the light. So the light's being reflected will have a certain polarization. By putting a polarizing filter on the camera, you can adjust it so as to minimize that particular light that's reflected. So then you stand a better chance of reading the barcode underneath. There are other ways of doing it, but that's a couple of examples there, really. Strobe lights, I borrowed some, I mentioned these already, I borrowed some from Hamamatsu at one time, and yeah, I mean, they're still used to some extent, and some people want to use them, but the idea is, I guess you have the camera in continuous acquisition mode, and then you flash the lights on as and when you want to check the position of something. This might have been popular years ago, because years ago they used to use TV standards for recovering the images in machine vision. Nowadays, we don't use TV standards for lots of reasons. We get higher resolutions with digital techniques, and we can use any resolution we want and just capture the image when we want to, rather than capture a series of TV kind of images. So we just capture the image when we want it. So nowadays, we'd have the lights on continuously, and we just capture the images when we want to see where the object is. So it's more of a practical approach, really. Now, this diagram here is showing the spectral response of the sensor in the camera. So you can see, sorry about the sort of double printing that happened here. I don't think that was a publisher who did that. Relative spectral response is up here, going up to 100%. And this is wavelength along the bottom in nanometers. So we're going from 400 up to 1,000 nanometers. So this is visible light. So visible light cuts off at about here, around about just below 700. So what we got here, as you can see, is that these sensors are more sensitive in this 500 sort of region, 500 odd region, than they are up here. Now, this can sometimes be a problem because, you know, one time we were doing a project for a company in the States. We were using laser triangulation to measure objects that were going to be air freight on aircraft. And we were using deep red. So we were using wavelengths about here. Okay. But the cameras we were using had this nuisance thing built into them called an IR cutoff filter. These were Sony cameras, but they felt obliged to put this IR cut. So this is an infrared cutoff filter. And the idea of it is, it sort of simulates the way the human eye works by cutting out wavelengths you can't see, because humans obviously can't see infrared. But the problem was that we wanted to image the light here, so we didn't want this cutoff because we were trying to get a good sensitivity like this. So what we did, we took out the IR cutoff filters, but that altered the focusing of the camera. So we had to buy from Sony some dummy filters and put them in place of the IR cutoff ones, which worked okay, and they got it working in the States. They're selling the system. They sold it to various airports around the world to measure freight. San Francisco Airport, Amsterdam, using the system now. But so what the upshot of all this is that when you're looking at an application, you want to think about the wavelength of the illumination you're going to use, and you want to look at the spectral response of the camera to make sure you get a decent response in that wavelength. So if we were looking at about 670, so up here we'd be okay with this sensor. This camera would be okay. If we were using this one, or particularly this one, we'd see we get virtually no signal here, so we'd have to be careful with that. So spectral response is an important characteristic of the camera. Now, yeah, so illumination outside the visible wavelengths can sometimes be useful. IR cutoff filter, I just mentioned that one. And then IR sources can be very useful in some applications. In fact, we use a technique called photometric stereo, which is a special technique we developed in the lab over the last 20 years. And it involves one camera and a set of lights. And we turn one light on at a time and capture a series of images, maybe at least 3, maybe 4 or 5, 6 images. And we use those images with what we call a lighting model to work out the surface orientation at each point on the surface. And that's the 3D data. And I'll talk about this in more detail later on. But we used it to develop a 3D vision system for airports with a company called General Dynamics, who've got a factory in South Wales. So we installed it down there and collected data down there. But yeah, it's a very useful technique, and it can enable you to recover 3D data very robustly and separate 2D and 3D data from surfaces. The reason I mention it is that when we started off using normal visible lights on it. We replaced it with infrared ones, near infrared ones, and then we found it worked much better. The technique when imaging the face with invisible illumination worked better than with visible. That's got a couple of advantages. Of course, we get better data, so we get a better reconstruction of the face. We also weren't bothering people around the apparatus. It was no longer flashing. They couldn't see the flash because it was infrared. And if you can recover the face in 3D, this has great advantages from the point of view of face recognition, because all these systems you see at the moment at the airport and so on, there are 2D systems, can all be fooled by just holding a photograph of somebody else in front of your face. So if you can recover the 3D morphology, that gives you additional useful information. It increases the number of applications because it increases the reliability of the face recognition from about 90% up to near 100, so lots of applications become possible. So we're trying to avoid shadows or glare. Poor lighting can cause problems. So as I say there, you can use specialized lighting and filters, all available from various vendors. Comar produce a lot of filters, which are very useful. We're Lender's filters that we can use. And Edmund Scientific have a vast array of filters and other optical equipment as well. They are a very big supplier. Now, thinking about the situation with the camera, so determining the field of view, so the camera has a sensor built into it. This is a schematic. There's a lens here, the optic as well. The focal length is the distance between the center of the lens and the sensor in the camera. This is expressed in millimeters. Then the field of view is how big an object you can image. So this would be the size of the thing you're trying to image. The focal distance is d there. So this is a little relationship of proportionality. Field of view equals the sensor size. This is just the dimensions of the side of the sensor again, not the area, times d over f. So that's pretty straightforward, and that's worth remembering and using that equation. That's an equation used all the time in machine vision applications. Yeah, in other words, when we're trying to get a setup to image something in the field, we have to think about this because we want to think about the type of lens that we're going to use. And also, it's a bit of a black art, really, because that's why we work a lot with these companies like Stemmer, because they've got a lot of experience in lens camera combinations. They know what works with what camera, what lens, and so they can give some good advice. For example, you have to get the right kind of lens for a given size of sensor, because if you had a very large sensor and a small lens mount, you would get vignetting and you wouldn't get a good effect. So you have to have all matched. Or if you've got a very, very high resolution sensor, then you need a sort of megapixel lens to go with it. Otherwise, you'd be wasting your money on an expensive sensor with a poor quality lens. So it's good to get them matched, really. Yeah, trying to get the glare out of it. Yeah, so we've got, as I mentioned, Edmund Scientific and Stemmer. Also, Stemmer, in the handbook, you'll see a vast amount of selection possibilities for lenses. Actually, we buy a lot of lenses, and we usually spend about as much on the lens as we do our cameras. We've got Schneider lenses in Germany, very high quality. There's a whole range of lenses. Sometimes a cheaper lens works well, actually. You don't have to necessarily spend thousands on a lens, but generally speaking, you want to err on the side of quality. So we're trying to acquire the image, and how do we actually acquire the image? So we've got to get the data from, obviously, the camera into the computer, and we've got to trigger it often as well. So how are we going to interface it, I suppose? How are we going to get this whole system working together? Well, nowadays, interfacing the camera and acquiring the image is relatively straightforward. Years ago, it used to be a bit complicated, just as a little bit of historical interest. We used to have analog cameras, which is a bit crazy, where we had a CCD producing a digital image, then convert that to an analog TV standard, then have an analog to digital converter in the frame grabber and convert it back, which was a bit crazy because you lost resolution, you got noise, so there wasn't a good idea, really. We used to have TV standards, of course, in UK it was PAL, in the States NTSC. And one good thing about it was we knew what we were doing with. We had a standard image size and we had a certain number of frames per second. But the limitations were more severe. I mean, nowadays you wouldn't bother with it because you want high resolutions, you want to get exactly what you need, you don't want to be limited by that. That's what we used to deal with years ago. Digital cameras over analog, so the advantage is then, well, we get a big signal to noise ratio, we don't have this analog stage. And as we say there, we can get all sorts of different resolutions, frame rates, and pixel depths, depending on the application we want. Sometimes that could be a slight disadvantage, actually, because maybe we got a bit too much variation and not enough standardization sometimes. But on the other hand, we can get exactly what we want for a given application. So this is showing the sensor on the printed circuit board, and then it's got the sensor, then you put an enclosure on it, you've got your camera. Digital cameras, we don't get any pixel jitter, don't lose that, high resolution. This is a bit out of date with 1,000 by 1,000. Nowadays, you'd be looking at more than that. You'd be looking at megapixels. And we used to use IEEE or FireWire connections, but again, nowadays you would go to, I think USB's one out over that. I'll come to USB 3. There are other ways of interfacing, of course. Monochrome and color cameras are available, and surprisingly, monochrome would be what you'd use a lot of times. You don't necessarily always need color at all in many applications. So you want to make it simple. You can use different resolutions of cameras, and when you buy a camera, you normally are thinking about resolution. You're thinking about megapixels, aren't you? But actually, when we're in machine vision, we're not necessarily looking at or requiring very high resolutions, because if you have a very high resolution image, you need a lot of processing to process just to do a filtering operation on it or something like that. So we don't need. It's important not to have more resolution than you need. So we find a lot of the time that 5 megapixels will give us many applications enough resolution. Another thing that's important that is often not mentioned is the size of the actual sensor. Because if you look at something like a digital SLR camera, you'll have quite a large sensor in it. That's because they want to have a nice, good quality image. Well, we want that in machine vision too. So a larger sensor with bigger pixels mean you get more light going in there, you get a better signal-to-noise ratio, and you get a better quality image. Generally speaking, you won't need such a small focal length on the lens, so you'll get less distortion as well. But of course, it costs more. Now, the two technologies that were typically used until recently in terms of these devices were a charge-coupled device and CMOS. Now, these work on a different type of electronics. Charge-coupled device is a TTL, and CMOS is CMOS electronics, which is lower voltage and lower power. So these had a good quality reputation years ago, and CMOS used to be thought of as a bit noisy. But nowadays, CMOS have come on a long way. I think even the sensors they use in digital SLR cameras nowadays are CMOS, and certainly the ones that you get in your smartphone, which, let's face it, gives you a pretty good quality image nowadays, is going to be a CMOS camera because it's lower power than CCD. Some people, maybe astronomers and so on, are still using CCDs, and they've certainly had a good, but they were very good and always offered good quality. So if you want to miniaturize an application like something like a phone, then you would certainly be looking at a CMOS camera. If you're in space and taking images from a spacecraft, you'd be looking at it as well, because of the lower power to make it more convenient than higher power devices. Interfacing to the PC, well, USB 3, of course, being pretty great, really, a lot of the time. Now, Camera Link is a high-performance interfacing technology that we still use, and it's good for very high gig data transfer rates. But it's a bit complicated, involving a specialized card, which would cost maybe up to £1,500 just installed in the computer. But why bother with that if you can do what you want with the USB camera? Or you could use a Gig E, of course, which has been very common. Coax Express is one that's also one that's very interesting because it's offering very high performance and long cable lengths. But to be honest, USB has come along so well and so standardized that I wouldn't be surprised if they don't all lose out to USB in terms of just simply connecting a camera, because you don't need any kind of technology other than just plug it into your computer. Now, what I've been talking about up to now is area scan cameras of the type you buy when you go and buy a camera in the shops or somewhere. But what's used a lot in industry is something called line scanning. Actually, that image didn't come out very well, did it? But I think this image here is better. So with line scanning, rather than having an array in the camera of pixels, you have just a line of pixels, 1 or 2 lines of pixels in the camera. And the idea is the object you're trying to image is going by on a conveyor belt. So rather than just capturing an image of it, you capture a line at a time. Now, I've been looking recently at some very high-speed document scanning capabilities. I bought these cameras, which are actually coming from Canada, and they're capable of 200,000 lines a second. Okay, and each lines are going to be up to like 8 megapixels long, 8 1,000 pixels long. So you can imagine you can get some pretty massive amounts of data coming off this technology. And it works, especially if you're trying to image things that are continuously coming along a conveyor, because it works better than an area scan, really, because with area scan, you get distortions up towards the corner of the image. You get something called barrel distortion due to the way the lens works. With this line, because you're just looking at a line, you get less distortion. It's more standardization. So the way it works is you have what they call an encoder on the conveyor belt, which measures the exact position of the conveyor. And then when it's in one position, you grab an image of the line. And then the conveyor moves a little bit, the encoder detects that, and you grab another image. So if the conveyor changes in speed, that will be accounted for because the encoder is measuring the actual position of the conveyor all the time. And you only need to flash a light every time you grab an image, so you can just use sort of LEDs that come on at that time. And it works pretty well in many industrial applications for objects coming along conveyor belts. The disadvantage of it is it's a bit complicated. It doesn't sound that bad, but you buy the cameras off one supplier, you buy the software from another supplier, you buy the frame grabbers from another supplier, and all of it's not necessarily that compatible. They're all talking, they don't necessarily want to, because they all prefer their own software and so on. So sometimes just getting simple things working, like getting images synchronized at high speed with the lights going on and off can be difficult. With the encoder can be difficult, surprisingly difficult. So it's a bit more complicated than just simply grabbing images on a conveyor, but with a normal camera. As I say, we can use different wavelengths of light, ultraviolet, infrared. We can reveal defects that are not visible with normal lighting. Then one thing you could do, for example, you could be inspecting fruit. And it turns out that if you've got an apple you're inspecting, the bruise on the apple is very visible in the infrared. So one camera we bought had two sensors in it, normal light and infrared. And we had a prism in there, splitting the light. So the light would come in through one lens, we split to two sensors. So you could get a normal image of the apple. You could also get the infrared image, which will show you where the bruising is, which will give you further information. So sometimes using different wavelengths can give you some very interesting information. You've got to be careful when you're using ultraviolet light, illumination of the shorter wavelength than visible, because that's damaging to the eyes. So you have to be very, very careful with that. Now, so that's a kind of introduction to the basics of image processing, which I hope you find some use. The other thing I've got on here is I put on the 2D and 3D face analysis for tickless travel paper, which I presented at a conference in Las Vegas in 2018. Now this I think is worth reading because talking about different wavelengths, we developed a system which is now operational in London. We developed it for the London Underground, and that's the version of it we had in the lab. So we developed it for the London Underground, and this uses a version of what this technique I was talking about, which is photometric stereo. So you can see here that the lights are illuminating the surface one at a time, turn them on one at a time, and you capture a set of images, and then you have a lighting model, which is a model of how the lighting angle affects the brightness you'd expect to see at a given point. And you apply that, and you've got three unknowns, okay? The surface orientation in two directions, surface normal we're talking about. This is the vector, which is normal to the surface. And then the actual pigment at that point, the reflectivity. And if we've got three or more light sources, we've got three unknowns, we can solve the problem. So what we do is we use this system to analyze people walking through on the way into the London Underground. So the reason I mentioned infrared, these are infrared lights, and they're synchronized with this high-speed camera here. So we're getting 3D data on the face as well as the normal image capture of the face. So by combining the 2D and the 3D, we get very robust face recognition. So you wouldn't have to mess around. This isn't actually operating on the London Underground because at the moment they seem to be quite happy, the company, probably still making money selling these gates, which are the paddle gates that you see at the Underground. All over the world they make them for, actually. But this system would be doing away with all that. So you can imagine at the rush hour how much easier it would be at Paddington or Victoria Station if you didn't have to mess around with that. It would be more like walking down, as though you were walking into a supermarket kind of entrance. And these systems would be operating without anybody even knowing about it. And just checking that the people who are meant to be traveling, the person they're seeing going in there is someone who's meant to be traveling at a given time. So the person would enroll with the system before travel. And this could be a very useful biometric. It could be very reliable. We demonstrated it works pretty well. And this paper gives you some information on what we did. So it talks about, I mean, one guy, when I was submitting this paper, one guy said, what about if you 3D printed your face? Could you use that to get through the system? Well, I think you'd have to be a bit crazy to want to go to that trouble. But even that wouldn't work, because why this works is that it works with a combination of 2D and 3D. So this is a dummy that we had, but you can see here, this is artificially colored, and the orientation of the surface normal is changing across the face, and the colors changing. So if you tried to fool the system by doing a 3D printing of the face, you'd need a 3D printing, okay? But you'd also have to have the 2D patterns. You'd have to somehow, which would be just virtually impossible, printing on, getting an accurate version of what the face looks like onto a model would be virtually impossible. So the chances of being able to spoof this system are very, very minimal. And we're not looking at any kind of big brother system with this. This is not a surveillance application. The idea here is to try to make people's lives easier. So it would only be used for people who want to use it. And it would only be used to detect people traveling onto this platform who, on a database of people who are meant to be traveling. You wouldn't keep a database of everybody in the country on this thing. You'd only keep the data for the people who are meant to be traveling at any given time, which has two advantages. First of all, you don't, from the point of view of personal privacy, you don't want your data to be kept all the time on the system. Secondly, if I'm trying to detect someone traveling, and I'm trying to detect them from the database of 1,000 people, that's much, much easier than trying to detect them for a database of 1 million people. So it also makes the pattern recognition much simpler. Another thing you can do, another thing I'm going to talk about in this course for doing things like face recognition, is apply something called deep learning. Because in our lab, we've got two niches, really. The first one's the 3D vision, captured using systems like this, which gives you lots of usefulness in many applications, which I'll talk about in more detail. But another technique which we're heavily into in the lab is deep learning. And most of the time we use a technique called convolutional neural networks. Now, I'll explain in more detail later on how a convolutional neural network works. But I'll probably start off by talking about how a regular normal neural network works. I don't know if you have any background in neural networks, but it's basically a pattern recognition technique which is data-driven, which is not prescriptive. So it doesn't look for features that somebody decides is a good feature for recognizing something. In the case of a convolutional neural network, it actually determines what the feature is itself. So because it determines the feature, rather than you having to sort of what they call handcraft it, that's less work for you. And also it's going to be much more reliable because it's based on the data rather than assumptions about what the features are. And that's one advantage of it. The other advantage is it's very, very powerful at pattern recognition. And that's why you hear so much about it. You hear so much about AI all the time, because this is probably the most significant breakthrough that's occurred in AI, is convolutional neural networks. So we find nowadays that the CNNs are perhaps even better than humans at recognizing patterns such as face recognition. So this is a big breakthrough that's occurred recently, and I think we could almost get quite good reliability by using that. But by combining that with these techniques I'm talking about here, with the 3D, we can really get very high reliability in face recognition. And this, of course, is a very good thing from the point of view of applications, because it means if we can go up towards 100% reliability, then the number of applications for this technology could really take off. And it could be, for example, that when you go shopping, if you wanted to, you wouldn't have to bother messing around with cards and pins and so on. You could simply use your face as a biometric. We did some work a while ago on the nose recognition part of it. I think I might have mentioned this before, but the nose is quite a good biometric. So that's additional reliability. You could, when you're at an ATM, you could forget about the pin and just use that kind of biometric to identify yourself. So it could be that it's a next generation, enabling the next generation of retail, which I think the high street needs, considering how a hard time it's having compared to online sales. But if we had a system whereby we remove all the instrumentation that you normally get, like checkouts and so on, and we simply we have a combination of lots of cameras for face recognition and deep learning for monitoring what people are doing in shops, then we can just automate the purchasing process for people who want to, they can just go in there, pick stuff up off shelves, and the system will know what's going on, charge it to their credit card. So there's all sorts of exciting possibilities, I think, with face recognition that could be achieved. It's really got to do with social acceptance of the technology, I guess. And it's hard to know what can and can't be done in certain applications at the moment, because the guidelines are not exactly sorted out, because there's still a bit of debate about where you should be in terms of consent in terms of these systems. For example, if you're in a supermarket trying to monitor people's behavior, it's not too clear about what conditions you can and can't use your vision system in, and where you might need consent for certain types of monitoring. So when that's holding companies back a little bit at the moment, I think. But there are still many, many applications that could employ this technology. Could be things like accessing a gym, rather than messing around with these fingerprint devices that they use at the moment, which actually, after someone's worked out, their fingerprint's different, so it may, because they've got more moisture in the skin, so it doesn't necessarily work very well at all. You just have a 3D system there, which gives you reliable access to a gym, that kind of thing. And people are implementing these kind of solutions at the moment. I think it's quite an exciting technology, because it's really got a massive potential application. So that's this week's lecture, really accommodated. I've got another paper which I did present to a conference which was going to be held in New York, but because of COVID, I had to do it in terms of recording. I might be able to put this recording, this other paper, for your information onto Blackboard. But what this was, it was very relevant to what I was just talking about, because it's a 3D face recognition research project, continuation of this work I'm talking about here. And the idea was that by getting the 3D face and changing the orientation, you can improve the reliability of the face recognition using deep learning. And also you can change the channels, the color channels information, and that will also give you improved learning. Because it's quite surprising with deep learning how you get yourself a bigger database just by editing the database you've already got, sort of changing the images in various ways. This is called data augmentation, and it works surprisingly well. You wouldn't necessarily think that was going to work, but it does work quite well. So I'll put that paper on, which I think is quite a nice 3D face recognition paper. And that'll be on Blackboard for you. If there's anything else you need me to do for you, got any other questions, just drop me an email and we'll sort it out. But I hope that was a reasonable introduction to machine vision for you. And I'll have another lecture for you next week. So I'll see you next week.